Hi there. Here's a little discussion on vector projection. Actually, also approved to the formula shown in the notes. But let's first get a pen here, and we're ready. So as we saw here, if you go back, vector projection can be found using this odd-looking formula here. Actually, I can collapse it to an even simpler formula. So it looks something like this. So the projection of vector, in this case, we want to project vector A on vector B. So you could say it's sort of like the shadow of vector A down here on B. So what we get is the vector here. So vector A on B. So we can write it like this: vector A projection on B, and the formula would be the scalar product of A and B. Let's make sure we do this right. Divided by the magnitude of B squared times the vector B. So what we should pay attention to is that all of this here is actually a scalar. So what we're doing is that we're scaling vector B, which makes sense. If this is vector B, we are sort of scaling vector B. We're finding a vector here, the projection vector, and it's parallel to vector B. So how do we get this odd-looking formula here? Well, let's have a look at it. So what we'll use is actually our knowledge of right-angled triangles here. We want to find the magnitude of that vector here, because we need that to scale the vector here, vector B. Also, we need to figure out a unit vector parallel to vector B. So it is a bit complex, but we are only using stuff that we know already. So first thing we could do is to find the magnitude of the projection here, and for that we will use the triangle OAX here. So we want to find the side OX, and since this is a right angle triangle, we can use the trigonometrical ratios here, and we know vector A, so we also know the magnitude of A, so that is our hypotenuse. What we want to find is the adjacent side here. So that would be the cosine formula, and the cosine of the angle here would be the adjacent side here, which is the magnitude of the projection, divided by the hypotenuse, which is the magnitude of A. So therefore, the magnitude of the projection will be cosine of the angle times the magnitude of A. Well, that is pretty straightforward, I guess. But we would perhaps like to know this in terms of the vectors and not so much the angle here. So it would be nice if we could replace the cosine by something else, and we want to look a bit like this. So it was something that uses the scalar product A dot B. There's a connection to the cosine and the scalar product, and you can recall perhaps that the scalar product is defined as the magnitude of A times the magnitude of B times cosine to the angle. So there's the connection directly. So therefore cosine is the scalar product divided by the magnitudes. So if we replace this notation here for cosine, we get that the magnitude of the projection is A dot B divided by A times the magnitude of B times the magnitude of A. So you can see here we divide by the magnitude of A and we multiply by it, so this cancels with this, and therefore the magnitude of the scalar product is A over it's A dot B divided by the magnitude of B. Yeah. So this is it's beginning to look a bit like this here. So this is an expression for the magnitude of the projection. So next we would like to find the unit vector parallel to vector B. So what we'll do is that we'll say, well, let's call it UB. It's the unit vector parallel to B. And recall that we can find a unit vector by saying the vector B divided by its own magnitude, or you could also say 1 divided by the magnitude B times B. We figured this out some lessons ago, that we can divide it by its own magnitude to find a unit vector. So if we use this here, this would be the unit vector that we need to scale by this here scalar. So therefore we can now simply multiply the scalar to this unit vector. So therefore we get that the projection vector is, well, the scalar here times the unit vector, and the unit vector in that form here is 1 over B times B. And if we simplify this, we get, well, you can see we multiply these two fractions here. We multiply numerator by numerator, so that's A dot B. And we go denominator by denominator, so that's magnitude B squared. And all that scalar is multiplied to the B vector. And this is actually the formula that we wanted to find, if you look back up here. So this is the projection